All right, folks, back here with what I hope is a quick video for you. One of the things I want to do is I need to introduce you to the fundamental theorem of calculus. And in order to prove the fundamental theorem of calculus, part 1 and 2, we're going to need to make use of what is called the area function. So in this video, I just want to go through real quick and show you the area function, folks, right? Break it down for you, work through an example, all right? And we're going to come back and use this in our fundamental theorem of calculus to help us develop it and, in a sense, prove the fundamental theorem of calculus. All right, let me grab my notes here, bring these over. Okay, so this is going to be a quick section on the area function, and as I begin with here, I just note we got to introduce this in order to introduce the fundamental theorem of calculus. All right, but where this does develop from is our understanding of the definite integral. All right, if this statement here, the definite integral from a to b for f of x dx, is the net area trapped by the function f of x over values of x in the interval from a to b, then if I play around with the variables a little bit in that statement, you can see what I'm going to do is I'm going to change the b into x, and I'm going to change the x into u, and what that does is it gives me what's going to produce a function of x. U is going to play the role of a dummy variable, where x is going to play the role of an independent variable in a function that describes area. All right, this here is a function that describes area. Again, the area now trapped between the function f of u and the u-axis over values of u in some interval from a to x. What's going on here in this calculation is a is being held constant, and our area is accumulating up to the value of x, whatever happens to be x, the independent value in this function. Right? And all of this is going to produce what's known as the area function. And that is what we formally define below here. Right? For f, a continuous function on some interval from a to b. Oh, I should be careful there. For f, a continuous function, I really probably should say here for x greater than or equal to a, the area function for f with left bound at a is given by a of x equal to the definite integral from a to x, little a to x, the left bound at a to the right bound at x, for what is going to be the function f at u, all integrated with respect to u, where maybe I should point out u is in this interval from a to x. Let's set it up this way. I don't know how that other way developed. I think I had an error in there. All right. Now, again, what this describes is an area function. Let me bring this up here. I do put this into other words to help us understand this a little better. Right? The area function is this function we call a of x. It is actually a dependent value. The area depends upon the independent variable x being the rightmost boundary on the trapped region. If we look down here at this illustration, this is what we're illustrating. We have our curve f, and here we have the area function described between the left boundary at A and this right boundary at X. This right boundary at X being just somewhere greater than or equal to A, to the right of it here, at any arbitrary location along the U-axis. If I stop it here at 2, that's going to give me the area up to 2, A of 2. If I stop X at 4, this would be the area up to 4, starting at A and continuing up to what would be that X value, that independent value of X. Right? That A of X describes the shaded region in the following illustration. The shaded region that starts at U equal to A here on the left and continues on to U equal to X on the right, where X is the independent value. Right? A of X depends upon the location of X that's bigger than A in this situation. Let's illustrate with an example here. I might say here, consider the area function for f of u equal to 1/2 u plus 5 with a left endpoint at a equal to 2. Well, in this case, my area function, a of x, is going to be the definite integral from 2 to x for my function f of u, which is 1/2 u plus 5, all integrated with respect to u. The value of this definite integral depends upon what I select for x to be this upper bound. And what we're considering now is the area that accumulates starting at 2 and continuing up to x, whatever x happens to be, this independent value. Well, in this particular case, this is a linear function, 1/2 u plus 5. And this area for an arbitrary value of x greater than 2, you can see here we have the left boundary on this region is at 2, and the right boundary is at this arbitrary value of x. It's right around 5 in my illustration, but it can be anywhere, right, as long as it's greater than 2. The area function that's going to describe the accumulating area underneath this graph, right, is going to be given by this definite integral, right, and going to describe the shaded region in this situation, where x is any arbitrary value, is any location greater than 2. It's the independent value. Well, if you take a look at this graph, or this shaded region, this area we're going to describe as the area of a trapezoid. And there's a formula for finding the area of a trapezoid back in geometry. The area of a trapezoid is going to be this length here from 2 to x times the average of the lengths for these two parallel sides. The side here at x and the side here at 2, these vertical lines that bound the left and the right of this trapezoid. If we take their average length and we multiply it by the length of the line from 2 to x, that's going to give me the area within this trapezoid. Take note here. The area of the trapezoid is described by the formula a equals 1/2. We call them base 1 and base 2. They're actually the two parallel sides. Right? When you add them together and you cut that in half, right, what you actually end up with is their average. And you're going to multiply that by the height, where the height in this case is going to be this measure from 2 to x. And if we set that up in this situation, h, the distance from 2 to x, is going to be x minus 2. b sub 1, this first space that's occurring at 2 is going to have a length determined by function f at 2. So if I plug 2 into my function, again, 2 is going to substitute in here. 2 times a half is 1, plus 5 gives us 6. This has a height that's 6. So this is, first base has a length of 6, where the second base at x has a length given by 1/2 x plus 5. The second base is just given by f at x, the quantity 1/2 x plus 5. So if I add these two bases together to begin averaging them, and divide that by 2, and then multiply that all by x minus 2, I'll have the area of that region. And in this case, the area function would be described by this quantity seen down here. This function of x seen down here. Here is the sum of 6 with 1/2 x plus 5. That becomes 1/2 x plus 11. 6 plus 5 are the like terms and add together to give you 11. When you cut that in half, you get their average. And then we multiply it by that height of x minus 2. That describes the area of that trapezoidal region, and that becomes the area function in this description. It's this function of x seen down here. And what you might notice is that function of x is actually a quadratic function, just it has been factored. So if we consider what's going to be the area trapped under this line, starting at 2 and ending at this independent value of x somewhere greater than 2, it will always be described by a quarter of x squared plus 5 times x minus 11. Substitute in where you end at for x, and this will give you the calculation for that area. Oop, how did I make that disappear? Let me bring that back in. Oop, too far. Right there, that's good. So let's look at a case. What if x was 8? What if I move this location to x down here so it's at 8? What would be the area trapped in this trapezoid? Well, that would be given by a of 8. Right? So if x is placed at 8, we would be at a of 8. And what we would be calculating is the definite integral from 2 to 8 then, in our area function, for 1/2 u plus 5, all integrated with respect to variable u. Which is this calculation seen up here, where x is just being replaced with the value of 8. And what do we know this is equal to in terms of x? Well, it's a quarter of x squared plus 5x minus 11. So if x is 8, it's going to be a quarter of 8 squared, which is 16. Plus 5 times 8, which is 40, minus 11. So this is going to be 56 minus 11, and what we end up with is an area of 45 units squared. Right? If we were to stop this x value down here at 8, there would be 45 square units of space underneath this, well, trapped by this graph, starting at the value of 2 and ending at that value of x equal to 8. If I would have stopped this x at 4, if I bring it back to 4, what would be the area inside there? Well, it would be A at 4. I plug 4 in here. That means 4 would go in here. That'd be 16. Cut into a fourth would be 4. Plug in 4 here, you'd have 20. So you'd have 4 plus 20 would be 24. And then take away 11, you'd have 13 units squared. And that would be the area of that portion of the trapezoid. That would be the area of that trapezoidal region that's forming under this curve, starting at the left boundary of 2 and continuing up to the value of x. Right? That is what we mean by an area function. Man, I am way off with this. Can I fix this real quick? Hold on. Yeah, there we go. A little bit more centered. All right. So you can see that calculation there for A at 8. All right. This is the area function, folks. We need to introduce this concept in order to begin discussing the fundamental theorem of calculus. The setup for the fundamental theorem of calculus to help us develop it is going to make use of the area function. And is going to make use of a setup that looks very similar to what we have going on here in this illustration. All right, folks. So as I had promised, this was going to be a quick video. We were just going to go through that one concept of the area function here, just to keep it brief and to keep it from making fundamental theorem of calculus too bulky. All right. But what we're going to come back to in the next video here is the video for the fundamental theorem of calculus. And I will end this video here, and I will see you in that next one.